December 1943. Bletchley Park, England. A windowless room hidden behind barbed wire and secrecy. Inside, a machine hummed to life. It was 10 feet tall, covered in wheels, switches, and vacuum tubes that glowed like tiny suns. Wires snaked across its frame like veins. Paper tape fed through its mechanisms with a mechanical whisper. The machine had no name yet. Its creators simply called it Heath Robinson, after a cartoonist known for absurdly complicated inventions. But this contraption was no joke. It was reading German military messages encrypted by the Lorenz cipher machine. Codes so complex that human mathematicians needed weeks to crack a single message. Heath Robinson processed the same information in hours. The machine wasn't just calculating. It was thinking, in its primitive way, following logical rules to expose patterns buried in chaos. This was the beginning, not of computers as tools, but as minds. Mechanical minds that could solve problems humans couldn't, that could remember perfectly, never tire, and work at speeds that made human thought seem glacial. The world didn't know it yet, but in that secret room, the future was being born. The idea of machines that could think was not new. For centuries, inventors had dreamed of mechanical calculators. Blaise Pascal built a brass calculator in 1642. Gottfried Leibniz improved it in 1673. Charles Babbage designed his analytical engine in the 1830s, a steam-powered computer that could theoretically perform any calculation if given the right instructions. But Babbage's machine was never completed. The technology didn't exist. The world wasn't ready. By the early 20th century, the pieces were finally falling into place. Boolean algebra, developed by George Boole in the 1850s, provided the mathematical foundation for logical operations. Vacuum tubes, invented in 1904, could act as electronic switches, turning electricity on and off at incredible speeds. Telecommunications technology demonstrated that information could be transmitted electronically over long distances. If you're fascinated by the hidden stories of inventions that transformed our world, subscribe to Retro Files and discover the forgotten moments that shaped modern life. What was missing was purpose. Mechanical calculators existed, but they were specialized tools for accountants and scientists. Nobody imagined a general-purpose thinking machine, a device that could be programmed to solve any problem, not just one specific task. World War II provided that purpose. War has always accelerated technology, and the Second World War was no exception. Governments poured unlimited resources into scientific research. Problems that seemed impossible suddenly had to be solved. Lives depended on it. Nations depended on it. The most urgent problem was breaking enemy codes. Modern warfare relied on encrypted communications. Armies, navies, and air forces transmitted orders, coordinates, and intelligence via radio. These messages were encrypted using mechanical cipher machines that scrambled text into meaningless gibberish. Without the correct key, decryption was mathematically impossible, or so it seemed. The Germans used two primary cipher systems. The Enigma machine, used by military and naval forces, was complex but could be broken through mathematical analysis and stolen intelligence. The Lorenz cipher machine, used for high-level communications between Hitler and his generals, was far more sophisticated. Messages encrypted with Lorenz contained 501 quadrillion, 942 trillion, 704 billion possible starting positions. Human mathematicians couldn't break it quickly enough to provide useful intelligence. British codebreakers at Bletchley Park needed a machine. They needed something that could test thousands of possible decryption keys per second, something that never made arithmetic errors, something that could work continuously without rest. They needed a computer, though that word didn't exist yet in its modern sense. Alan Turing was already at Bletchley Park. A brilliant mathematician from Cambridge, Turing had published a theoretical paper in 1936 describing what he called a universal machine, a device that could simulate any other machine by reading instructions from tape. It was pure theory, a thought experiment about the nature of computation itself. Turing never expected anyone to build such a machine. But in 1943, the theoretical became necessary. Tommy Flowers, a telephone engineer, proposed building an electronic machine to break Lorenz ciphers. His design used vacuum tubes, thousands of them, to perform logical operations at electronic speeds. Military officials were skeptical. Vacuum tubes were unreliable. They burned out frequently. A machine with hundreds of tubes would fail constantly. Flowers disagreed. He argued that tubes failed primarily when turned on and off repeatedly. If kept running continuously, they were remarkably stable. He convinced his superiors to let him try. Working in secret at the Post Office Research Station in London, Flowers and his team spent 11 months building the machine that would be called Colossus. Colossus was delivered to Bletchley Park in December 1943. It contained 1,500 vacuum tubes, more than any previous electronic device. It was programmed by physically rewiring plug boards and adjusting switches. It read encrypted messages from paper tape that moved through optical readers at 5,000 characters per second. And it worked. Colossus could break a Lorenz cipher in hours instead of weeks. By war's end, 10 Colossus machines were operational at Bletchley Park, breaking thousands of German messages and providing Allied commanders with invaluable intelligence. General Eisenhower later said that ultra-intelligence, the code word for information derived from breaking German ciphers, shortened the war in Europe by at least 2 years. But Colossus was a secret. After the war, Winston Churchill ordered the machines destroyed and all documentation burned. The engineers who built Colossus were sworn to secrecy and forbidden from discussing their work. For decades, the world didn't know that Britain had built the first programmable electronic computer. While Colossus remained hidden, America was building its own computer revolution, and this one would not be secret. In 1943, the U.S. Army commissioned the University of Pennsylvania to build a machine for calculating artillery firing tables. Artillery accuracy depended on complex mathematical calculations accounting for angle, distance, wind, temperature, and projectile characteristics. Human computers, mostly women trained in mathematics, performed these calculations by hand using mechanical calculators. It was slow, tedious work. The Army needed firing tables for hundreds of weapons, and human computers couldn't produce them fast enough. John Mauchly, a physicist, and J. Presper Eckert, an engineer, proposed building an electronic calculator that could perform the computations at unprecedented speeds. Their design called for nearly 18,000 vacuum tubes, more than 10 times the number in Colossus. Army officials were skeptical, but desperate. They approved funding. Construction began in 1943 at the University of Pennsylvania's Moore School of Electrical Engineering. The machine was called ENIAC, Electronic Numerical Integrator and Computer. It would be the first general-purpose electronic computer capable of being reprogrammed to solve different types of problems. Building ENIAC was extraordinarily difficult. Nobody had built anything like it. Every component had to be designed from scratch. Vacuum tubes had to be tested individually. Of the initial batch, 20% were defective. Power supplies had to be custom-built to handle enormous electrical loads. Cooling systems had to prevent the machine from overheating. Wiring had to be planned in intricate detail. Miles of wire connected thousands of components. The work continued through 1944 and into 1945. Germany surrendered in May 1945, meaning ENIAC arrived too late to serve its original purpose. But the machine was completed anyway. On February 14, 1946, ENIAC was publicly unveiled at the University of Pennsylvania. ENIAC was monstrous. It filled a room 30 feet by 50 feet. It weighed 30 tons. It consumed 150 kilowatts of electricity, enough to power 50 homes. Its 18,000 vacuum tubes generated so much heat that the room had to be continuously cooled. When turned on, ENIAC reportedly dimmed the lights in the entire neighborhood. But ENIAC was also miraculous. It could perform 5,000 additions per second. It could multiply two 10-digit numbers in 3 milliseconds. It could calculate a trajectory in 30 seconds that took a human computer 20 hours. For the first time, a machine could think faster than the person who built it. The public demonstration was carefully staged. ENIAC calculated the trajectory of an artillery shell and displayed the results on lights and printouts. Journalists and military officials watched in amazement as the machine performed calculations too fast for human observers to follow. The New York Times called it an amazing machine which applies electronic speeds for the first time to mathematical tasks hitherto too difficult and cumbersome for solution. ENIAC made computing real. Colossus had been secret. ENIAC was public, celebrated, and undeniably impressive. It proved that electronic computers were possible and practical. Scientists and engineers around the world suddenly understood that computing machines represented a genuine technological revolution. But ENIAC had serious limitations. Programming, it was nightmarishly difficult. The machine had no memory for storing programs. Instructions had to be manually set by plugging cables and setting thousands of switches, a process that could take days. ENIAC was programmable in theory, but reprogramming it was so laborious that it was practically a special-purpose machine, rebuilt for each new problem. The solution to this problem came from an unexpected source. John von Neumann, a Hungarian mathematician working on the atomic bomb project, visited the ENIAC team in 1944. Von Neumann was a genius who could comprehend complex systems instantly. He recognized ENIAC's fundamental weakness. Programs and data were separate. Programs were hardwired into the machine's configuration. Data was fed in during operation. Von Neumann proposed a revolutionary idea: store programs in memory alongside data. Instead of rewiring the machine for each new task, simply load different instructions into memory. The machine would read its own program, interpret instructions, and execute them automatically. This concept, the stored program architecture, would become the foundation of all modern computers. Von Neumann documented this architecture in a report called First Draft of a Report on the EDVAC, written in 1945. EDVAC, Electronic Discrete Variable Automatic Computer, was the planned successor to ENIAC, designed to implement the stored program concept. Von Neumann's report was distributed to scientists and engineers, spreading the ideas rapidly. There was controversy. Von Neumann's name was on the report, leading many to credit him solely with the stored program concept. But Mauchly and Eckert claimed they had already conceived similar ideas before von Neumann's involvement. The truth is complex. The stored program architecture emerged from collaborative discussions among multiple brilliant minds. History would call it the von Neumann architecture, anyway, cementing his name to the concept. By 1950, the computer revolution was underway, but computers remained rare, expensive, and incomprehensible to ordinary people. Perhaps a dozen operational computers existed worldwide. They filled entire rooms. They required teams of specialists to operate. They cost hundreds of thousands of dollars. They were tools for governments, universities, and large corporations, not for individuals. Yet the implications were already becoming clear. Computers could perform calculations that would take human mathematicians years. They could simulate complex physical systems. They could process vast amounts of data quickly and accurately. The question was no longer whether computers were useful, but how far their capabilities could extend. The early 1950s saw rapid development. The University of Cambridge completed EDSAC, Electronic Delay Storage Automatic Calculator, in May 1949. It was the first practical stored program computer, implementing von Neumann's architecture. EDSAC used mercury delay lines for memory, a technology borrowed from radar systems. Sound pulses traveling through tubes of mercury represented data, circulating continuously to preserve information. Mercury delay lines were clever but impractical. They were slow, unreliable, and limited in capacity. EDSAC's memory held about 512 words, barely enough for small programs. But it proved the stored program concept worked. Programmers could write instructions, load them into memory, and let the machine execute automatically. For more untold stories of the inventions that shaped the digital age, subscribe to Retro Files and explore the moments that transformed how humanity thinks. At the same time, researchers were developing better memory technologies. MIT built Whirlwind, a computer using magnetic core memory, tiny magnetic rings threaded with wires. Each core could be magnetized in one of two directions, representing 0 or 1. Core memory was faster, more reliable, and more capacious than mercury delay lines. By the mid-1950s, magnetic core became the standard memory technology, remaining dominant for 2 decades. The computers of the early 1950s were still massive and expensive. UNIVAC I, Universal Automatic Computer, delivered to the U.S. Census Bureau in 1951, weighed 16,000 pounds and cost over $1 million. It used 5,200 vacuum tubes and required constant maintenance. but it was also the first computer sold commercially. Business and government customers began ordering UNIVACs, recognizing their potential for data processing. UNIVAC gained public fame in November 1952 when CBS News used it to predict the presidential election. With only 7% of votes counted, UNIVAC predicted an Eisenhower landslide, 438 electoral votes to Stevenson's 93. The prediction seemed absurd. Polls had suggested a close race. CBS producers, doubting the computer, didn't air the prediction. But when the final count confirmed UNIVAC's forecast almost exactly, the computer became a celebrity. It had demonstrated knowledge beyond human intuition. It had seen patterns invisible to experts. This moment marked a shift in public perception. Computers were no longer just calculating machines. They were oracles, possessing insight that transcended mere arithmetic. People began attributing intelligence to computers, even though the machines were simply following mathematical algorithms. The 1950s also saw the first serious thinking about artificial intelligence. In 1950, Alan Turing published Computing Machinery and Intelligence, proposing what became known as the Turing test. Turing asked, "Can machines think?" He argued the question was meaningless without a clear definition of thinking. Instead, he proposed a practical test. If a machine could converse with humans through text, and humans couldn't distinguish it from another human, then the machine could be said to think. Turing's paper inspired a generation of researchers to pursue artificial intelligence. The term artificial intelligence was coined in 1956 at a conference at Dartmouth College. Researchers including John McCarthy, Marvin Minsky, and Claude Shannon gathered to discuss whether machines could be made to simulate every aspect of human intelligence. The mood was optimistic. Many believed human-level artificial intelligence was perhaps 20 years away. They were wrong. Artificial intelligence would prove far more difficult than anyone imagined. But the pursuit drove computer development forward. Researchers needed faster computers with more memory to experiment with AI algorithms. Each generation of computers enabled more sophisticated experiments. The transistor, invented at Bell Labs in 1947, would transform computing. Transistors were solid-state devices that could switch electronic signals on and off, just like vacuum tubes, but they were smaller, more reliable, used less power, and generated less heat. Initially, transistors were expensive and difficult to manufacture consistently. But by the late 1950s, production techniques improved and costs dropped. The first transistorized computers appeared in the late 1950s. They were dramatically smaller and more reliable than vacuum tube machines. The IBM 7090, released in 1959, used transistors and could perform 229,000 calculations per second, 40 times faster than UNIVAC. NASA used IBM 7090s for orbital calculations during the Mercury space program. The transistor had made computers fast enough and reliable enough for real-time applications where human lives depended on correct calculations. But computers remained isolated tools, each machine operating independently. Programs and data couldn't easily move between different computers. Each manufacturer used proprietary designs and formats. A program written for an IBM computer wouldn't run on a UNIVAC. Computing was fragmented. IBM addressed this problem in 1964 with the System/360, a family of compatible computers spanning different price and performance levels. Programs written for one System/360 model would run on any other model. Customers could start with a small, affordable system and upgrade to larger, more powerful models as their needs grew without rewriting software. This compatibility was revolutionary. It established the concept of a computing platform, a stable foundation for software development. The System/360 required an enormous development effort. IBM spent $5 billion, more than the Manhattan Project cost. The company bet its future on the success of System/360. If it failed, IBM would likely collapse. But it succeeded spectacularly. System/360 dominated business computing through the 1960s and 1970s. IBM's competitors struggled to match its capabilities. Meanwhile, computer programming was evolving. Early computers were programmed in machine language, numeric codes directly representing hardware operations. Programming was tedious and error-prone. A single wrong number could crash the entire system. Only specialists with deep technical knowledge could program computers. Assembly language improved the situation slightly. Instead of numeric codes, programmers used mnemonic abbreviations, ADD, instead of a number representing the addition operation. Assembly language was still tied closely to hardware, but it was more readable and less error-prone than pure machine code. The real breakthrough came with high-level programming languages. Fortran, formula translation, developed by IBM in the late 1950s, allowed programmers to write mathematical formulas in a notation resembling algebra. A compiler translated Fortran code into machine language automatically. Programmers could focus on problem-solving rather than hardware details. COBOL, Common Business-Oriented Language, emerged in 1959 for business data processing. Grace Hopper, a naval officer and computer scientist, was instrumental in developing COBOL. She advocated for programming languages using English-like syntax that business people could read and understand. COBOL became the dominant language for business applications, remaining in widespread use for decades. These languages democratized programming. Scientists, engineers, and business analysts could write programs without becoming hardware experts. Computing was no longer the exclusive domain of specialists. This accessibility accelerated software development and expanded the range of problems computers could address. But computers were still expensive and centralized. Organizations had one or a few computers, typically housed in climate-controlled rooms. Users submitted programs and data on punched cards. Computer operators loaded the cards, ran the programs, and returned results hours or days later. Computing was a batch process, not interactive. Users couldn't see their programs run or debug problems in real time. Time-sharing systems, developed in the 1960s, changed this. Multiple users could connect to a single computer through terminals, keyboards, and displays connected via telephone lines. The computer rapidly switched between users, giving each the illusion of having the machine to themselves. Users could type commands, see immediate results, and interactively develop and test programs. Time-sharing made computing personal for the first time. Each user had their own account, files, and working environment. Computing transformed from submitting jobs to operators into a direct, interactive experience. This shift was psychologically profound. Computers were no longer distant oracles that provided answers to questions submitted in advance. They were responsive tools that reacted to user input immediately. The 1960s also saw computers entering unexpected domains. Computer-generated music, art, and animation began appearing. Researchers explored using computers for creative purposes, not just calculation. Computers controlled machinery in factories. They managed airline reservations. They processed banking transactions. Computing was infiltrating every sector of the economy and every aspect of institutional life. But ordinary individuals still had no access to computers. Computing remained institutional. You needed to work for a university, corporation, or government agency to use a computer. The idea that individuals might own personal computers seemed absurd. Computers were too expensive, too large, too complex. They were infrastructure like power plants or telephone exchanges, not consumer products. This began changing in the late 1960s and early 1970s with mini computers. Companies like Digital Equipment Corporation built smaller, cheaper computers aimed at departmental use rather than organizational mainframes. A mini computer might cost $20,000 instead of millions. It could fit in an office instead of requiring a dedicated building. Smaller organizations could afford computing. The integrated circuit, invented in 1958, made mini computers possible. Instead of discrete transistors wired together, multiple transistors could be fabricated on a single silicon chip. Early integrated circuits contained just a few transistors. But manufacturing techniques rapidly improved. By the late 1960s, chips contained hundreds of transistors. By the early 1970s, thousands. The microprocessor, introduced by Intel in 1971, integrated an entire computer's central processing unit onto a single chip. The Intel 4004 contained 2,300 transistors and could execute 60,000 operations per second. It was designed for calculators, but represented a revolutionary concept, a complete computer on a chip. Within a few years, microprocessors became powerful enough for general-purpose computing. The Intel 8080, released in 1974, became the heart of the first personal computers. These were not mass-market consumer products yet, but hobbyist machines sold as kits. Enthusiasts soldered together circuit boards, wrote their own software, and explored the possibilities of personal computing. The Altair 8800, introduced in January 1975, became the first commercially successful personal computer. It was primitive, no keyboard, no screen, just switches and lights on the front panel. Programming required toggling switches to enter binary code, but it cost only $400 as a kit, making computing accessible to individuals for the first time. The Altair created a community. Hobbyist computer clubs formed across America. Members shared designs, software, and ideas. They believed computers should be personal, accessible, and empowering. This was a radical departure from institutional computing, where specialists controlled access and determined what problems were worth solving. Two young men in Silicon Valley saw the Altair's potential. Steve Wozniak, an engineer at Hewlett-Packard, designed a more capable computer as a personal project. His design included a keyboard, video output, and elegant engineering that minimized chip count. Steve Jobs, Wozniak's friend, saw commercial potential. In 1976, they founded Apple Computer and began selling Wozniak's design as the Apple I. The Apple II, released in 1977, transformed personal computing from hobbyist curiosity into mainstream possibility. Unlike the Apple I, which was essentially a circuit board requiring technical knowledge to use, the Apple II was a complete system in a plastic case. It had color graphics, sound, and expansion slots for adding capabilities. Most importantly, it could run VisiCalc, the first spreadsheet program. VisiCalc gave business professionals a reason to buy personal computers. Accountants, financial analysts, and small business owners who had no interest in programming suddenly needed an Apple II to run spreadsheets. What had been an expensive toy became an essential business tool. The personal computer industry exploded. By 1980, hundreds of thousands of personal computers were in use. By 1985, millions. IBM entered the personal computer market in 1981 with the IBM PC. IBM's involvement legitimized personal computing for corporate buyers who viewed hobbyist machines as toys. The IBM PC used an Intel processor and Microsoft's DOS operating system. IBM published the PC's technical specifications, allowing other companies to build compatible machines. This openness created a massive ecosystem of IBM-compatible computers, software, and peripherals. Microsoft, founded by Bill Gates and Paul Allen in 1975, became the dominant software company by providing the operating system for IBM PCs and compatibles. MS-DOS was crude compared to more sophisticated systems, but it was good enough and ubiquitous. As personal computers multiplied, Microsoft's position strengthened. By the mid-1980s, most personal computers ran Microsoft software. To dive deeper into the stories of invention that quietly rewired civilization, subscribe to Retro Files and discover the forgotten experiments that shaped our modern world. Apple took a different path. In 1984, Apple released the Macintosh, featuring a graphical user interface with windows, icons, and a mouse. The Mac was inspired by work done at Xerox PARC in the 1970s, where researchers had developed the first graphical interfaces and mouse-driven computing. Apple refined these concepts for mass-market use. The Macintosh was revolutionary but initially unsuccessful. It was expensive, underpowered, and incompatible with the dominant IBM PC platform. But it established principles that would eventually define all personal computing. Computers should be intuitive, visual, and accessible to non-technical users. Computing should feel natural, not like operating machinery. By the mid-1980s, personal computers were common in offices and increasingly present in homes. Children grew up with computers in classrooms. Video games on computers and dedicated consoles became a major entertainment industry. Computers were no longer exotic. They were becoming ordinary. This familiarity changed how people thought. The generation raised with computers processed information differently than previous generations. They were comfortable with abstract symbolic manipulation. They expected instant responses to queries. They thought in terms of files, folders, and hierarchical organization. Their mental models of how things worked were shaped by computer interfaces. Programming became a widespread skill. Millions of people learned BASIC, the beginner-friendly programming language included with most personal computers. Children wrote simple games and programs. Adults automated work tasks. Programming demystified computers. When you could write code and make the computer do what you wanted, you understood that computers were tools, not magic. But as computers became more powerful and software more complex, fewer users programmed. Early personal computer users had to understand some programming and technical details. But as software improved, computing became more appliance-like. Users consumed software created by professionals rather than creating their own. By the 1990s, most computer users never wrote a line of code. The internet transformed computing from an individual tool into a communications medium. The internet had existed since the 1960s as a military and academic network, but it remained obscure until the 1990s. The World Wide Web, created by Tim Berners-Lee in 1989, made the internet accessible through graphical browsers. Suddenly, computers were portals to a global network of information. The web exploded in the mid-1990s. Websites proliferated. Email became ubiquitous. Online commerce emerged. Social interaction began moving online. The internet wasn't just another computer application. It fundamentally changed what computers were for. They became communication devices, information access tools, and social platforms. This shift accelerated changes in human cognition and behavior. Attention spans shortened as people learned to skim web pages rather than read deeply. Multitasking became normal, multiple browser tabs, email, instant messaging, all running simultaneously. Information became instantly accessible, reducing the need to memorize facts. The emphasis shifted from knowing information to knowing how to find information. Search engines like Google, founded in 1998, changed how people interacted with knowledge. Instead of navigating hierarchical structures or consulting reference books, users typed questions into search boxes and received instant answers.